So I have three exciting problems to go over today regarding thermodynamic processes. The first one involves adding quite a bit of heat, 860 kilocalories, to some gas being held at a constant pressure. As a result, the volume will have to increase from 4 cubic meters to 7.8 cubic meters, so this is the largest piston in the world apparently. Anyway, we want to find the work done by the gas. So in this case, if we have an isobaric process, we can find the work. You can look at that little table of that cheat sheet I showed you in the other video. The work done is P delta V. The pressure we're holding constant is 1 atmosphere, but we need to be careful with our units. If we're finding work, we want that to be in joules, so we need standard units. So 1 atmosphere, we need to convert that to pascals, which is equivalent to a Newton per meter squared. So we multiply that by 1.013 times 10 to the 5th pascals per atmosphere, or Newton per meter squared per atmosphere. So that big ugly thing is our pressure. Our change in volume, these are already in standard units, so that's nice. We can just have 7.3 minus 4.0 and throw that puppy in your calculator, and you get a whopping 384,940 joules of work. So if this were a piston, it would be pushing on something and doing that many joules of work as it expanded. Now we want to find the change in internal energy of the gas. Well, the change in internal energy is equal to Q minus W. We already have W, so we're going to plug that number in here. Q is given 860 kilocalories. Again, though, we have to be careful with units. We can't add joules and kilocalories, or subtract in this case. So our conversion factor here is 4,186 joules per 1 kilocalorie. CAL. Alright, so those are going to cancel. That's going to be one term, and then we're just going to subtract off this nice little amount here. Multiply that guy. Gives you another very large number, in fact even larger, 3,599,960 joules of heat, minus this rather measly looking number now, and we are left with a total change in internal energy of 3,215,020 joules. So hopefully this helps you see what we're talking about with this delta U equals Q minus W. We're putting energy in when we're letting heat flow in, but then if it does work with some of that energy, it pushes on something else. Essentially it uses or transfers some of that energy to something else, not necessarily as heat, not as heat in fact, but it did some work. And then the leftover, the net of those processes, is the change in internal or thermal energy. Okay, question number 2. We've got 2 liters of gas at 2 atmospheres, expanded, blah, blah, blah. And I want you to make a PV diagram for this situation. You're going to be making quite a few PV diagrams. You might get a little sick of them. Such is the nature of your education. I'm so sorry. Alright, so I'm going to start out here. I'm at the point 2,2, and if I think about where I'm going to go, I can kind of decide which corner of the graph I want to start in. I'm going to expand isobarically, so that's constant pressure, and then I'm going to compress isothermally. So isothermal is going to head this way. Anyway, kind of think ahead. I'm going to start here at the point 2,2. This is in atmospheres. You can go ahead and leave your PV diagrams in whatever units you're given. What did we say? Liters here? Okay, liters. My dot went away. I don't know why it does that. Okay, so we start out isobaric expansion to twice its original volume, so we're going to end up over here at 4. Isobaric means we are horizontal, not changing the pressure. We're going to draw a little arrow saying that that's the direction we went. Then we're going to compress, so the volume will shrink back to its original volume. So I'm going to come back to 2. Now we know this has got to be an inverse graph, so we're going to go up here. And because of the way inverse graphs work, if I ended at 4 there, that means I'm going to be at 4 here if I'm holding everything constant but pressure and volume. Try to make a nice little curve here. Draw an arrow on it. We went up there, so that's our isotherm. And then finally the pressure is returned to 2 atmospheres in an isovolumetric process. So constant volume means it's vertical, and we're going back down here to 2. So we went around our nice little loop. And there you have it. Beautiful PV diagram. Last one, we have a 2-step process. Heat is flowing out of an ideal gas. Basically, all of these things are assuming ideal gases. Sometimes we'll state it explicitly, a lot of times we won't, but assume it's ideal anyway. Okay, so the pressure drops from 2.6 to 1.8, then it expands, blah, 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 blah. We want to calculate all this stuff. Okay, I would start out, even if it's not asking you to, I would draw a PV diagram anyway, because they are useful tools. So we start out here, and we're going to at 2.6, then we're going to drop down here to 1.8. 8, there we go. So that's our first process. And then this was at a volume of 5.8. Keep drawing 5 is where my H should be. That time it erased it nicely for me. And then we're going to go over here to 8.3, not exactly to scale. Anyway, those are the 2 steps. We don't always have to have a complete cycle. That's fine. We've got step 1 here, step 2 there. And we want to know the total work done by the gas. Well, you might say, I don't know how to find the total work for everything. Well, you just have to find the work for each process and then add them together. And the work done here, delta V is 0, so the work is 0 for this part. So that part is nice and easy. And then we want the work done here. I'm going to go over here and just give myself a little more room. It's P delta V. So that's easy enough. 1.8 times the change in volume. The pressure was atmospheres. Change in volume was liters. So we do have units to worry about, as always. So I've got 1.8 atmospheres. I'm going to multiply by that 1.013 times 10 to the 5th conversion factor. So this is going to give me my pressure in newtons per square meter, or pascals. And then my change in volume, I'm going to have 8.3 minus 5.8. Those are liters, and I want this in cubic meters. Now there's 1,000 liters in a cubic meter, so I'm going to divide that by 1,000. I could divide them each by 1,000 or just do it at one big happy time here. And we find the work here is 455.9 joules. And that change in volume was positive. You always do final minus initial, so be careful with your signs on these. I will get upset if you have negatives when you shouldn't, or if you are missing them when you should have them. Okay, change in temperature of the gas for the process. Ooh, change in temperature. Oh, it's kind of tricky. Our equation of delta U equals, looking ugly, Q minus W. There's no T in there, and even if we plug in P delta V for W, we still don't have a T in there. So whenever we're talking about temperature, you need to think of our old equation with a couple deltas thrown in there. Delta U equals 3/2 NK delta T. Now, in the entire process, we have a couple of different things going on. We've got our isovolumetric and our isobaric, and you might think, I don't really know how to find delta U, because that's what we need to find delta T. For either of those things, so you might be a little stumped at first, but the hint here, the trick here, is that the temperature reaches its original value. So when we're here, we're at some temperature, T1, we end up at some other temperature here, T2, and then when we're over here at some new temperature, T3, we're told that T1 equals T3. So that is the key here. So for the entire process, earlier I said sometimes you want to look at each leg of the process. Here we want to look at the whole thing. We end up at the same temperature where we started. So delta T for the entire process has got to equal 0. So we didn't even need to find delta U. We just say 0. Done. Okay. Essentially, these lie along an isothermal line, even though they didn't travel along that line to get there. There's still a inverse curve here. Didn't really draw that well. Okay, last question. What is the total heat flow into or out of the gas? So now we are looking for Q. We just said that delta T is 0, and if delta T is 0, then our good friend delta U is 0. If delta U is 0, then delta U equals Q minus W. That guy's 0. This becomes Q equals W, and we already have W. Don't need to change any signs here. So Q is also equal to 455.9 joules. So in the process, we have this much heat flow in because it's positive. We also do this much work because the work is also positive. All right, have fun calculating thermodynamic processes.